Welcome back. In today's lecture, I'm going to cover power cycles. This will be the last lecture on the series of the second law of thermodynamics, which we are trying to revise related to the engineering thermodynamic aspects of the course. So, we have discussed earlier about the Carnot cycle, which apparently is the most efficient cycle between two specified thermodynamic limits, but there we have tried to use something of that order of gases, but if you consider the working fluid ways there is a phase transition along the process, then one can consider again this Carnot cycle within dome of the phase transition. So, this is typically the diagram of T and S, and this would be your Carnot cycle considering your isothermal and adiabatic processes. So, and this is a case for the steam as a working fluid. Now, this has an issue, particularly if you consider this as the specific cycle where you have this liquid to gas vaporization, then you have expansion, and then again some kind of condensation, and you have compression isentropically. So, if you consider this thing, the question is that is it a suitable model for power cycle, that is a cycle which generates power. So, that could be what typically we consider in a steam based power plant. Okay. So, there are impracticality associated with considering such a Carnot cycle. We call it Carnot vapor cycle. The reason is that it limits when you consider this 2 point here, that means it the phase transition or the latent heat along this transition is equivalent to the heat which you can get, or that means it limits the heat transfer, because this will be your simply delta H. Now, that is clearly one of the limits. So, that means it's a limited thermal efficiency because of these constraints. Other issues is that the turbine cannot handle low quality steams. Okay. The second is the compressor cannot easily handle two phase compression, which is the case here. Though the Carnot cycle we talked about as the most efficient cycle, but when it comes to the power cycles, the Carnot cycle cannot be approximated in the actual device, and it certainly is not realistic model in this case. Okay. So, you cannot just have 4 processes of isothermal and adiabatic form in the way we have learned as far as that is concerned. So, what we do, we try to modify a bit of that, and that is we can do that. We can play with bringing this 1 to 2 process at very high end to avoid this phase transition. So, we can play with that. Okay. But the better one is cycle is designed as a Rankine cycle, which is a ideal cycle for vapor power cycles. Okay. So, here what we have is we have a system. So, this is should be this. Okay. And there is a boiler here, okay, which brings a Q in. So, this represent the Rankine cycle device set of devices and the processes. So, what we do is by, so we do not want to do the solution which we have offered and possibly heating it to the superheating. That means you are operating at much higher pressure for the boiler, which can cause a lot of money and basically could be an inefficient process in the end. So, here what is done is differently. So, if you look at the system here, the set of processes. So, let us start with the pump here. Okay. So, here the saturated liquid enters the pump. So, the corresponding to is somewhere here. So, this is your 2 here. Okay. So, this is the 2 part, this is the 1 to 2 is your basically pump here. So, the numbers have got messed up, but let me try to explain this. So, this is the point, because saturated liquid enters the pump. Okay, the pump is this. So, this is the saturated liquid line. So, this is the saturated liquid line, this is the saturated vapor line. From here it went to the higher pressure line, this is the higher pressure line. Okay, and this is the pressure of the boiler also. So, this goes to the boiler at that pressure, and then that heat is being supplied to the boiler, which is your Q in. Okay, so it appears little bit shift in this value. So, this must be Q in. Okay, and this one is basically your Q out. Okay. So the Q in is being provided here. So this goes to the superheated region, and that is where the 4 is here, and this is where it's basically given to the turbine, where there is fluid expand, the steam basically expands, and what you get is something, this point which has a very close to the saturated line, okay, and then it gets condensed to the saturated liquid point here. Okay, so this is the complete cycle here. So this is what we call it a Rankine cycle. This is something which you have already went through in the last in your engineering thermodynamics class. If not, we will try to do some examples on it. So if you look at this 1 to 2 is isentropic compression in the pump. Pumps operate at a constant entropy. Okay, so this is a pump, constant entropy. Then constant pressure, heat addition in the boiler. So heat is at a constant pressure. This is the boiler. Then isentropic expansion in the turbine. So turbine here gets expanded, the gas here the steam here gets expanded in the turbine, and the constant pressure heat rejection in the condenser. So this is a constant pressure. So that's what you look at it. Okay. So this is a complete cycle here. This is an ideal Rankine cycle relevant for your steam engines. Okay. So one can now apply energy balances on each of the devices. So again, this is something missed out here. So this is the boiler. Okay. So this is the boiler. Okay. And this is heat being provided, Q in. Okay, and this is your Q out. So if you apply energy balance, then essentially it will be something like this: Q in minus Q out plus W in minus W out, and that must be same as the enthalpy, because of the fact that this is a flow system. So the fluid keeps flowing, and hence you have to look into the delta H here. So for the case of pump, the Q is 0, is adiabatic, that is why we consider this an isentropic process. The W pump in is nothing but the change in the enthalpy. So this is 4, 3, this is 1, this is 2. So it's going to be simply delta H2 minus H1, that is the W pump in. For the case of boiler, the work is 0, okay, and hence I am going to just consider the Q in, okay, and the Q out is of course we consider 0. So Q in nothing, Q in, okay, Q in is nothing but 4 minus 2. So this is 1, 2, 1. So this is 1 here. So this will be 1 actually. This will be 2. This will be 3, and this will be 4. Okay. So if you look at it here, the boiler would be simply 3 minus 2. That is what it is. Turbine is going to be 3 minus 4 because it's expanded. So essentially this 3 is going to be having a higher enthalpy, and condenser is going to be 4 minus 1. So that is the right hand side part. The left hand side, of course, if you look at the turbine is a Q in, the turbine is W out, and boiler is Q in, and the condenser is Q out. So this is a basic energy balance. If you put it down there, it should be okay. So this you can ignore because there is some change in the or shift in the values which was put in here because of the compatibility issues. Okay. Anyway, so I hope you understand. So again, let me just revise just to make sure we are on the same page. So you have a pump, you have a boiler, you have a turbine, you have a condenser. The boiler has Q in, is being supplied Q in, and the Q in, if you do energy balance on that, Q in is nothing but H3 minus H2. Okay, for the turbine there is a W out. Okay, W out is nothing but H3 minus H4. Okay, based on basic energy balance here. And similarly, Q out is nothing but H4 minus H1. And W in, which is a work on the needed by the pump, is going to be simply H2 minus H1. So that is the basic energy balance. Okay. Now, in order to find the thermal efficiency, we know that W net divided by Q in is efficiency, and this is something which we know that you can use the total energy balance of the system, which is going to be 1 minus Q out by Q in. Okay. So W net is nothing but Q in minus Q out, which is nothing but the work of turbine out minus work of pump in. Okay. So that is something based on simple energy balance. So let's now try to solve a problem which is the usual generative idle Rankine cycle problem which is considered. So this is little complicated, not the straight problem, but I thought this is a good problem where you can consider all aspect of what we do in such kind of power cycle analysis. So this is a steam power plant that operates on the idle regenerative Rankine cycle. Now with a closed feed water heater, okay, as shown in the figure, the plant maintains the turbine inlet. Okay, so it maintains the turbine inlet. Turbine inlet is 4 at 3 megapascal, right, or 300 kilopascal and 350 degrees Celsius, and it operates the condenser at 20 kilopascal. Steam is extracted at 1000 kilopascal. So to serve the closed feed water heater. So this is the feed water heater. So it is at this, which discharged into the condenser after discharged. Okay, so this comes here in the closed water heater, which is nothing but a heat exchanger kind of thing. Okay, where it is here, but it goes up there and then is put back into the condenser. But then if you look at it, there is a valve here which basically is nothing but expansion valve. So it is throttled, okay, to the condenser pressure. So the pressure remains same, but here the pressure gets changed to that of the condenser. Okay, so calculate the work produced by the turbine, the work consumed by the pump, and the heat supplied in the boiler for this cycle. Basically you have to do all analysis of it. So you have to find WT out, you have to find condenser pump in, okay, and you have to find the Q in also, okay, for this cycle per unit of the boiler flow rate. So assuming some simple flow rate, we will be considering that. Okay, so let us look at it very carefully. So what we have is, if you look at it, I have drawn directly this. We can start with a simple phase diagram, TS diagram, and this is your basically binodal curve, saturated line, vapor, and then we just consider from this one, which is nothing but here. Okay, this is the saturated liquid inlet to the pump, and then is the second the stream goes to the closed feed water heater. So here if you look at, this is one, and this is a adiabatic process, that is what we are assuming it for the pump. So it's isentropically pressurized, okay, at 2. Now 2 is basically the pressure at which the boiler works, okay, 3 megapascal. Okay, so from here what we are doing is, it goes to 3, and the 3 it happens here. So 1, 2 and 3 is here. 3 is at the boiler pressure. So essentially 3 is somewhere here. Okay, but it will be also at 1 megapascal the pressure which is maintained because of this. Okay, so this turbine goes here, and this is the pressure we are getting from the feed water heater. Okay, so this is your megapascal part here. So from here 1 to 2, 2 to 3, it goes to 4 superheated region, and then at 5, because it has extract a certain amount of the steam at 1 megapascal. Okay, so this 5 is being mixed with, basically if you look at it, not mixed, if the 5 is taken out, and then essentially it is 5 is here. Okay, so 5 is here, and then it goes to, if you look at it, 7. So 5 to 7 is there, that is where it basically throttles. So 5 to 7 here. So in this process the steam basically loses the energy, okay, because it's here what we are getting is a saturated system, and then in the closed water heater it goes to this point which is saturated liquid, and then it throttles, so essentially it goes to the it expands, and from 7 to 8 it drops down the pressure. Okay, so we have drawn this line, but essentially we don't know. So we from 7 to 8 somewhere, this is on this 20 kilopascal saturated line. Okay, that is your 8 here, and that goes to the condenser, and then it 6 and 8 get mixed, and what we get is 1. Okay, so 6 and 8 get mixed, and what you get is 1. So this is a complete cycle. It's a little complicated, but something worth discussing, this kind of problem, which is more common. So let us now try to solve this problem. So one we know from the saturated liquid part. So from the table, now this table I have taken from the book, but you can take it from any steam tables, and so this is just illustrative numbers, which should not change much from the steam table to steam table. So this is H1 is nothing but the fluid enthalpy at 20 kilopascal, which we know. Similarly, the specific volume would also be the specific volume of the fluid at 20 kilopascal, which is this. So this is the information of one state which we know. Now, in order to find WP in, okay, we can use directly the S2 minus H, the delta H, but we also know that for the case of the compressor work, it is nothing but the volume VdP also. Okay, so this is something which we know for such a compressor work. Okay, considering that a V, because it's a fluid, is a constant, then simply we can write it as this. Okay, so that comes out to be WP in minus PV1, but this is also same as S2 minus H1. Okay, so by this we can find out precisely S2, because otherwise we don't know the S2. So using the information of the pressure, now we know the amount of the work which is being done here, W pump in. Okay, so this would be your V delta P. This is also S2 minus H1. So from here we can obtain the value of S2, and that is this. So we calculate this and obtain the value of S2. Okay, so now the question is like from here, essentially we want to find out the work consumed by the pump. That anyway we have done that. We need to find out the heat supply in the boiler. That means we need to obtain many more things actually. So let us go systematically. Let us find out the states of the 4 and 5 first, before we try to solve the heat supply to the turbine, heat supply to the boiler, and other part of the questions. So we know the state 4. So state 4 is basically at 3 megapascal and 350 degrees Celsius. Okay, so for that we have H4 information from the table and from S4, and as well as the entropy part. So the 4 is 300 megapascal, okay, and 350 degrees Celsius. So this is directly from the thing. The plant maintains the turbine inlet at 3 megapascal and 350 degrees Celsius. So that information is used here to obtain the enthalpy and entropy from table. Okay, so here we are going to use the superheated table at 3 megapascal, and corresponding to 350 you obtain this. Now what is your state 5? State 5 is at 1 megapascal, but since it's an isentropic process, because it is taken out from the turbine, S5 is going to be S4. So you have now P5, which is a 1 megapascal, and then you look at this S4, and from the table, now it's going to be saturated table. Okay, so from this saturated table, pressure table, you can find out what is the appropriate enthalpy for H5. So you may have to do some interpolation again from table. Okay, but in this case, saturated pressure table. Okay, so you have the information of 5. Now similarly you also can obtain information for state 6. P6 is to 20 kilopascal we know, and as well as we know that is also an isentropic process, because is further down the line in the pressure, so with a lower value of X. So from here we can find out also the quality. So you can actually get S6 directly. So a typical exercise would be something like this. You know S6 because S6 is nothing but S4. Okay, and you know at the saturation pressure table. Okay, you can obtain from there SF and SG, and you can use this SF here and as well as SFG, which is the difference between the two. So, obtain the quality, and then you can write down H6 as HF plus H6 multiplied by HFG. Okay, from there you can obtain this also. So, similar way actually we have done this also. Okay. Now, you have the information of 5, you have the information of 6, what about 7? For an ideal closed feed water heater, the feed water is heated to the exit temperature of the extracted steam, okay, which ideally leaves the heater as a saturated liquid at the extraction pressure. So, this is the ideal closed feed water heater. So, this is something which we have to consider in this particular problem, that P7, okay, which is this here, P7 which is this here, this 7, this is the steam which is extracted, and then the one which is here, this will be of course a saturated liquid with a X close to 1, but when it exits from the closed feed water heat, the pressure is still going to be 1 megapascal, but the quality of this should be 0, because it will be saturated liquid. That is what the ideal feed water heater is this. So, that is what we consider is. So, if you consider this, then this is nothing going to be saturated liquid, okay, and the temperature corresponding to that would be this 179.9 degrees Celsius. So, this is something which we have done that. So, from here 5 to 7 we have shown this as on the saturated liquid, because this is the ideal feed water heater. Okay. So, now with this information you know the 7, but what about 8? Now, from 7 to 8, that means we are using the expansion here. So, it is throttle using the throttling valve. So, 7 to 8 occur, we know that this process will be at constant enthalpy. So, H7 is equal to same as S7 is basically equal to H8. So, you have this information here, okay, and what remains now is basically the P3, which we have not talked about. Now, P3 is going to be same as that of P3 will be on the same temperature as that of 7. So, P3 should be 3 megapascal and T3 should be same as T7. So, there is a typo here, but it should be same as T7, and based on this information you can obtain S3. Okay. So, now you have basically the information of all the information of the state, and you can now start doing a bit of analysis. So, one of the things which you can do is to apply energy balance over the heat exchanger, that is feed water heater. So, we know that for the basic energy balance is going to be Mi dot Hi is equal to Me He, and this is that M5 H5 plus M2 H2, that is the 5 and 2 streams which comes in 5 and 2 is the inlet feed, and 3 and 7 are the outlet feed. So, essentially I am going to use that to expand this. So, this is what we get. Now, this is a one, so the flow rate is a constant. So, we can assume this flow rate. So, we can consider that as, and we know that using a basis for that, one can show that this is nothing but if you consider a split of y goes to 5. So, that means the y fraction of the stream is now in the feed 5. So, y H5 plus 1 H2, 1 is a basis here, it should be equal to 1 H3 plus y H5. So, this y we do not know, we can calculate this. If you rearrange this thing, then essentially we know this y is this, because we have calculated all the enthalpies. So, again y is something like this. So, y goes here for steam 5, and okay, so the rest, so this is your turbine, okay. So, y goes here in steam in the stream 5, and 1 minus y, the remaining one goes as stream 6. So, if you do this energy balance, so the mass balance, because of the fact that we are considering is just a basis of 1, let us say kg per hour as a basis, and then essentially we can show this, that this can be simply written in this way. From here we can get the y, and once we know the y, we have everything. So, let us demonstrate that. So, W turbine out is going to be, if you look at this, W turbine out is going to be 4. Okay, so H4 minus basically this term. Okay, and if you rearrange H5 and H6, you can obtain H4 minus H5 plus 1 minus Y H5 minus H6. So that is going to be WT turbine. Similarly, pump in, we already know, we have done that because we can use simply V delta P. For Q in, for the turbine, so for the boiler, is going to be H4 minus H3. So turbine, so this is your 3, so this is your Q in. So Q in is nothing but H4 minus H3, and that's, you're going to get this expression. Now you can obtain the W net, which is W net turbine out minus WPN, and then you obtain this value, and from here you can get the efficiency of this particular ideal regenerative Rankine cycle. So that is a very, of course, cumbersome, but it's a careful exercise. One has to make sure that you have the information, the right states or the properties of the exit and inlet conditions for different devices, and make use of the steam to find out the relevant questions here. Okay, so I will just quickly go through this consideration of analysis of power cycle, which we often make use of it. Most of the cases it is not going to be a straightforward. Many times we use ideal cycle just the way we have done it in ideal regenerative cycle. Usually in ideal cycle we will be assuming it to be internally reversible processes. So for example, if you consider a pressure versus volume, the actual cycle may be in the dashed line, but the ideal cycle will be in this way, right? So this is an approximation we often use in order to solve the problem. Okay, so which essentially means that all our calculations which usually will have a higher efficiency, and the actual may be much lower. So I can skip this part. We already know the ideal cycles are internally reversible, but unlike the Carnot cycle is total reversible. That means it is also externally reversible. The ideal cycles are not necessarily externally reversible. So that is something which we can remember that. Okay. So what are the common idealization and simplification in ideal cycle or power cycles? So we assume that the cycle does not involve any friction. Therefore, the working fluid does not experience any pressure drop as in flow in pipes or devices. All expansion and compression processes take place in a quasi-equilibrium manner. Okay, so in a sense we are considering internally reversible process, and the pipes connecting the various components of the system are all well insulated, and heat transfer through them is negligible. Okay, so that's something we use it as an approximation. Many times we use a property diagram which serves very valuable aid. For example, if you consider this PV, then this process here, the cycle here, the area under this curve is nothing but W net. Okay, and similarly for TS also it shows that. So essentially it's because very valuable to just diagrammatically find out what is the net work done, okay, and which will be of course will be equivalent to the net heat transfer for a cycle. Okay, so that becomes very valuable exercise. So as we have already discussed, a Carnot cycle is a valuable tool for analysis and gives a limit as far as efficiencies are concerned, and this we know that it can be written in this way for a given two limits of the temperatures or the sources. Okay. Okay, so now we have done this exercise for ranking cycle. Now we can do the similar exercise for refrigerated cycle, okay, which is a reverse of what as far as the cycle is concerned. So here of course we are not going to use boiler, we will be having evaporator, okay, and we will not use turbine, we will be using a valve. Okay, so this is a typical refrigerated cycle. Okay, so this is the refrigerator unit which we would like to maintain at a temperature, and this is evaporator which takes out the heat, okay, and then it passed to a compressor, and this is the compressor basically pumps this particular fluid, working fluid, to a very high pressure of the condenser, which finally condenses to a saturated liquid. Okay, and from there we get a expansion valve brings to the basically saturated liquid vapor state. So if you look at it, this is the one which is saturated liquid vapor state, and is evaporated further, it gives a saturated vapor, and pumped more to a higher temperature, which is 3, and then it condenses to 4. Okay. So let's now solve this problem based on this understanding. This is a desired, so it's an example of refrigeration cycle. So it is desired to produce 10 kilowatt of refrigeration from a vapor compression refrigeration cycle. So what we have just shown is nothing but a vapor compression refrigeration cycle. Why vapor compression? Because this is kind of saturated vapor, okay, and this is basically compressed here. So and then this is condenser. So this whole process entirely depends on from going from 2 to 3, so that we can extract. So this is one of the key element in the process, and hence the name is for. Okay, so let's go back to the question. It is desired to produce 10 kilowatt of refrigeration from a vapor compression refrigeration cycle. So the working fluid is the refrigerant 134A. The cycle operates between 120 kilopascal and 900 kilopascal. Assuming an ideal cycle, determine the coefficient of performance and the mass flow rate of refrigerant needed. The property of the refrigerant is given here, which we have taken from the Weber book of NIST, which is a very valuable resource for thermodynamic data. Okay, so the couple of things which we have already made this here. So if you look at it, the pressure 0.12, this is something which is the working fluid. The pressure, if you look at it, the pressure here is going to be less, okay. This is going to be 3 to 4 is going to be much higher. So these are two different limits of the pressure. So let's look at it. This is 0.12 and 0.9. The cycle operates between two pressures, okay. So it's like this one, and then this, okay. So this is another pressure. So these are two different limits of the pressure, 1 and 2. So now we need to find out COP. So in order to get COP, we need to obtain the condenser heat associated with that means we need to find QC, and we need to find the work which we have done, Q. So this is a desired output, and this is a required input, okay. So that is your coefficient of performance, and hence we need to find these two variables. So let us look at the energy balance first. So we will do the energy balance on evaporator. So if you do energy balance here, so this is going to be QC is the flow rate S2 minus H1, right. So this will be molar flow rate, let's say molar rate. And what about WC? WC is going to be N dot H3 minus H2, okay. So these are the two things. The other thing is that this must be also adiabatic, so it's an asymptotic process. So S3 is equal to S2, and also is that throttling should occur at constant enthalpy. So H4 should be equal to H1, okay. And COP is nothing but QC by WC is H2 minus H1 divided by S3 minus H2. So basically this is our expression to find it out, okay. So now the question is, how do you get this variable? So let's look at it. What we have 0.9 megapascal, the saturated liquid enthalpy is H4, and that should be saturated liquid enthalpy. This is what it is. This must be same as H1. So essentially I can write this S2 minus H4, S3 minus S2. What about S2? S2 is saturated vapor at 0.12. So that is also given to us, saturated vapor at 0.12, that is S2. So essentially I know this. So I have the value of QC. So this is something I know this, so I have the value of QC. What about WC? So in order to calculate WC, so WC is what I don't know at this point. So WC
is nothing but S3 minus S2. Okay, S2 we know. So how do you calculate S3? So S3 is here. So S3 is nothing but at 0.9 megapascal. Okay, 0.93 megapascal, and this is the entropy is same. So essentially S3 and S2 entropy is same. S2 is given here. So S2 entropy is this. Okay, at this condition this information is given. So this must be same as S3. So if you look at the steam table, so at 177.89 joules per mole Kelvin, this is your entropy. So if you look at it, the corresponding temperature we can get, that is going to be 176.2. From the superheated steam pressure table, you obtain the temperature as well as you obtain the H of that is 43.578. Okay, so this is your kilojoules per mole. Okay, so from here this is nothing but H3. So you plug in here this information in COP. Okay, because now you obtain the COP easily by knowing all this value. So if you plug in this, you can find out this is going to be 3.22. Okay, so that is the information. Based on this, that is the value which we have just calculated from a rigorous analysis. Okay, so what we have done is very straightforward. You had a table which is given to you, and you know the final states of 1 and 2, 3, 4, and then you made use of the information such as the isentropic is an isentropic process, and the enthalpy is going to be constant for the case of the valve. For the case of compressor, it's going to be isentropic process, and hence you know this conditions, and you have applied that and you obtain the value of QC and WC, and subsequently you know the COP from this exercise. Okay, so I think these exercises will illustrate the use of the learning which we have done in last few lectures, and with this we will be closing the second law applications, and then we will move to a new set of lectures from next week onward. So I will see you in the next week.